Light from the sun takes about 8 minutes to reach your eyes. That means right now, you're never actually seeing the sun as it is this second. You're seeing it as it was 8 minutes ago. And here's the stranger part. 8 minutes is fast. Light is the fastest thing in the entire universe. Nothing. Not a spaceship, not a signal, not even gravity can outrun it. Except this year, scientists found something that technically did. And it did it without breaking any rules at all. Today, we're explaining the speed of light in plain, simple words. Why it's the universe's ultimate limit, what would really happen if you got close to it, and that strange new discovery that made headlines this year. Welcome back. I'm David. This is SciTales. Segment 1. Let's start with the number itself. Light travels at about 300,000 kilometers every single second. To put that in perspective, light could travel around the entire Earth about 7.5 times in 1 second. In the time it took you to read that sentence out loud, light could have circled the planet dozens of times. Now, here's the part that took science a long time to fully accept. That speed isn't just really fast. It's a hard ceiling. Nothing with mass, no object, no spaceship, no person, can ever reach it, let alone beat it. Why? Here's the simple way to picture it. Imagine pushing a shopping cart. The faster it goes, the more effort it takes to speed it up further. Now imagine that effect, getting more and more extreme the closer you get to light speed, to the point where, right before you'd reach it, it would take an infinite amount of energy to push any further. There isn't enough energy in the entire universe to get a single solid object all the way up to light speed. That's not a technology problem we might solve one day with better engines. It's baked into how energy and speed relate to each other. This idea comes from Albert Einstein, and it's called special relativity, which sounds intimidating, but the core idea is simple. The laws of physics work the same for everyone, everywhere, and the speed of light in empty space is always the same number, no matter how fast you yourself are moving. That second part is the strange one. If you're in a car and you turn on your headlights, the light doesn't leave your headlights faster because your car is already moving. It leaves at the same fixed speed, no matter what. Segment 2. And this is where things stop feeling like normal, everyday physics. If the speed of light has to stay the same for everyone, no matter how fast they're moving, then something else has to give. And that something is time itself. Here's the simple version. The closer you get to the speed of light, the slower time passes for you, compared to someone who stayed still. Scientists call this time dilation, but you can just think of it as speed bends time. This isn't a theory that's never been tested. We test it constantly. Astronauts on the International Space Station are moving fast enough that their clocks run very slightly slower than clocks on Earth. So slightly that after spending time in orbit, astronauts end up a tiny, tiny fraction of a second younger than they would have been if they'd stayed home. It's a real, measured effect, not a guess. Now stretch that idea to an extreme. If you somehow boarded a spaceship that could travel at 99% of the speed of light and flew away for what felt like 1 year to you, decades could pass back on Earth. You'd step off that ship and find your friends and family had aged far more than you had. You wouldn't have traveled to the future using some kind of magic. You'd have gotten there simply by moving very, very fast, and time doing exactly what physics says it should do. And this is also why light speed itself is such a hard boundary. If you could somehow reach it completely, time would stop advancing for you altogether, from your own point of view. Light itself, in a very real sense, doesn't experience time passing at all as it travels. That's not poetry. It falls directly out of the same math that gives us GPS satellites that actually work correctly. Segment 3. And now, the news story that makes this episode worth making right now. In March of 2026, a team of physicists, led by researchers at the Technion in Israel, working with scientists from Harvard, MIT, and Stanford, published a study with a headline that sounds impossible. They measured something moving faster than light. Here's what actually happened. In simple terms, light waves aren't perfectly smooth. If you look closely enough, you'll find tiny pinpricks of complete darkness scattered inside them. Spots where the wave briefly cancels itself out to nothing. Scientists call these dark points or vortices. You can picture them like the little swirling holes you sometimes see in a river, or the eye of a whirlpool in your bathtub. Back in the 1970s, physicists predicted something strange about these dark points. Because they're not physical objects but rather a kind of pattern in the wave, they might be able to drift through the light faster than the light itself moves. Nobody had ever managed to actually see it happen. The whole thing unfolds far too fast, over spans of time too tiny to capture, even with a very good camera. This year, using an extremely fast, specially built microscope, the team finally recorded it directly. Roughly a third of the dark points they tracked really were moving faster than light, some of them reaching just over the actual speed of light itself. So does this break Einstein's rule? No, and this is the important part. These dark points aren't things. They don't carry any mass. They don't carry any energy. They don't carry any information from one place to another. They're simply a pattern shifting through the wave. The same way a shadow can race across a wall faster than any object is actually moving, if you shine a light at just the right angle. Nothing solid is truly making that trip. Only the pattern is moving that fast, and Einstein's speed limit only applies to things that are actually carrying mass, energy, or a message. So the real headline isn't "Physics was wrong." It's physicists finally built a camera fast enough to film something we predicted 50 years ago, and it behaved exactly as expected. That's a genuine win for science, just not the rule-breaking headline it first sounds like. Segment 4. So why should any of this matter to someone who isn't a physicist? Because this one speed limit quietly shapes almost everything about how the universe works. It's the reason the sunlight warming your skin right now left the sun 8 minutes ago. It's the reason the GPS app on your phone has to correct for time moving slightly differently for satellites in orbit, or your location would drift off by miles within a single day. It's the reason that if we ever detected a signal from an alien civilization on a planet 1,000 light-years away, we'd actually be watching a message sent 1,000 years in our past. The speed of light isn't just a number in a textbook. It's the universe's built-in delivery limit for information itself, the fastest that cause can ever turn into effect, anywhere, for anyone. Every signal, every bit of light, every piece of information in existence is bound by it. And the astronauts quietly aging a fraction of a second slower than the rest of us are living, breathing proof that it's real. Let's bring it home, in plain words. The speed of light, about 300,000 kilometers per second, isn't just fast. It's the fixed speed limit of the entire universe, and nothing with mass can ever reach it. Get close to it, and time itself slows down for you. An effect we've actually measured with real astronauts. And this year, scientists filmed tiny dark points inside light waves, briefly outrunning light itself, not by breaking the rule, but by being patterns instead of objects, which the rule was never written to cover in the first place. Science isn't about a list of unbreakable facts sitting untouched forever. It's about testing the edges of what we think we know, and finding out we were right in ways even stranger than we expected. Next episode, we're heading into the darkest objects in the universe, black holes. What they actually are, what would really happen if you fell into one, and why even light itself can't escape. I'm David. Thanks for listening. Stay curious.